we're going to continue our discussion from the previous video. So at the end of the previous video, we observed that in D4 of this matrix, there are 24 terms, and each term you get one element from each row and each column. As a result, you get 4 factorial, which is 24 terms. The question is, how do we determine the sign in front of each term? Now, if you had a chance to look at this, you might have figured it out already. Or you might have found the answer from the internet through a search. And the key is to look at the inversions. What do I mean by inversion? Anytime you pick 2 indices, if the indices are not in ascending order, that's called an inversion. For example, if I look at these 2, I have 3 and then 2. 2 appears after 3 here, but 2 is less than 3. So we flag that as an inversion. Now, same thing with this pair. If you look at these 2, I have a 4 and a 2. Again, there's an inversion. And there's no other inversion. So there are 2 inversions here for this term. And what about this term here? Well, there's only one inversion, and it appears in the last 2 elements, 4 and 3. And if you look at this term here, I have all kinds of inversion. I have 4, 2, 4, 3, 4, 1, and 2, 1, and 3, 1. So 1, 2, 3, 4, 5. 5 inversions. And you notice that if the number of inversions is odd, the sign is minus. And if the number of inversions is even, like this term here, the sign is a plus. And you can check that for all terms here. So let's check one more term. So if we look at this term, there's an inversion 2, 1, 4, 1, and 4, 3. So there are 3 inversions. So you get a minus sign in front. Alright. So if you go to the 3 by 3 case, it's the same. So I have 1, 2, 3, there's no inversion here, so it's plus. But here, in the second term here, I have 1 inversion, and there's 3, 2. So the sign is minus. And if you look at this, we have 1 inversion, it's 2, 1. Again, it's minus, and so on. And for the 2 by 2 case, that's easy to check too. So based on the patterns that we have seen in D2, D3, and D4, a reasonable thing to define Dn is the following. So let A be an n by n matrix, and we're going to label the ij entry as Aij, and we're going to define Dn of A to be this minus 1 to the number of inversions of the permutation times A1 sigma 1 up to An sigma n. Alright, so what does that mean? Usually a permutation is given by something like this. So for example, when n is 4, a permutation is usually denoted as this. It means that if you want to look at sigma 2, well, you look at the column here, there's the element 2 in the first row, and the result is 1. So basically what it is saying is the second element gets mapped to 1. And if you look at sigma of 3, that would be 2. And so in this case, the number of inversions of this sigma will be what? I have a 3, 2 as an inversion. I have 3, 1 as an inversion. And that's it. So for this sigma, the number of inversions is actually even. And so this will be a plus. So this definition of Dn will be consistent with our D2, D3, and D4. And so the question now is, given Ax equal to B, where A is this n by n matrix, and B is B1 up to Bn, and that this system has a unique solution, what can we say about the solution X? Well, what we really would like to say is the following. We hope that this definition of Dn will be consistent with what we have obtained for the 2 by 2, 3 by 3, and 4 by 4 cases. Let me write this down here. we want xi to be given by dn of ai divided by dn of a, where ai is obtained from a by replacing column I with the tuple B. We know that this is true for 2 by 2, 3 by 3, and 4 by 4. But we really want this to be true for all n, because otherwise this definition doesn't really extend the pattern. It turns out that this is true, and this is what is known as the Cramer's rule. And the proof is not too difficult, it's just a lot of messy calculations. And we can also conclude that if you are just given ax equal to b, then it has a unique solution if and only if dn of a is non-zero. And this is what we call the determinant. So when you see determinant of a where a is n by n, we are really talking about the dn of a as we have defined here. Now, if you pick an arbitrary textbook on linear algebra, very likely that you won't see this here as the definition of the determinant. And there are good reasons for that. Calculating the determinant using this formula is actually quite cumbersome. For example, if you look at a 5 by 5 matrix, to compute the determinant using this formula already requires 120 terms. But one can routinely compute determinants by hand for 5 by 5 matrices. So there are a few things about determinants that we need to establish to make the computation easier. And we'll explore these properties in the next videos.